SPG. Today we have a presentation from Urs Schaltegger from the University of Geneva. It's ID-TIMS LA-ICPMS zircon uranium lead dating, advances, advantages, challenges, and limitations compared. So today Jim Gutowski is going to give the introduction for Urs. So please go ahead, Jim.
It is my pleasure to introduce Professor Urs Schaltegger, the head of the isotope geochemistry group at the University of Geneva, Switzerland. He obtained his PhD in 1989 from the University of Bern in Switzerland. From 1989 to 1996, he held postdoctoral research fellowships at institutions such as the Royal Ontario Museum Geochronology Laboratory, the Australian National University, the CNRS Center for Surface Geochemistry, and ETH Zurich. He joined ETH Zurich as a senior researcher and lecturer from 1997 until 2001. In 2001, he joined the faculty at the University of Geneva. His research interests include developing state-of-the-art analytical techniques for high-precision uranium lead dating, studying timescales for the formation of large igneous provinces and their intercalibration with periods of mass extinction, calibrating geological timescales by uranium lead dating of zircon found in volcanic ash beds, and timing and tempo of magnetism in the Earth's crust. We're looking forward to this talk. Please take it away.
Thank you. So, hi to everybody. It's a big pleasure to be able to speak to you, to give this talk. So it will be already apologizing, it will be a bit technical probably. And maybe start with a very general question. Why do we actually want to do geochronology? So we would like to date crystallization of zircon, of an igneous rock maybe. We would like to temporarily correlate events, as James was mentioning, between large igneous provinces and biotic events, for instance. We would like to calibrate durations and rates of magmatic processes. And we will see how these two methods are useful to address some of these questions, and maybe some of these, or one of these methods is less useful than the other. So I have to go a bit into the technical details. So I would like to acknowledge people from the isotope group in Geneva and also the petrology group in Lausanne, where I do the laser ablation dating in the LA-ICPMS lab of Alexei Ulyanov. So I want to start with this CL image. This is a high-resolution CL image of the Pleszowice zircon. This is an international reference material, and you will meet this name many times in this talk because it's used as a standard for laser ablation dating. So now this doesn't work. No, sorry.
Just not switching slides properly, or?
Oh, it does not switch slides at all. It's completely stuck.
Maybe try ending the slideshow and just jumping back in, because I know it worked before, right?
It did, yes. But the only thing I did is switch to the laser pointer. Okay. Okay. Obviously, he doesn't like this.
Okay.
Okay, so I will give very little background, some basic background, just very shortly, and then speak about the two techniques. So first ID-TIMS and then laser ablation ICPMS dating. First, address some issues of sample selection, preparation, imaging, more specific topics like chemical abrasion for the ID-TIMS standards, the choice of how and why do we use standards for laser ablation ICPMS, but then also address questions of precision, accuracy, presentation and interpreting data, and also limitations of the two techniques, which then will guide me directly to comparison of the two techniques. So I'll show you a few case studies where I have data from both of these techniques and how they compare, and end up with conclusions and also an outlook which should be positive and not only criticism. So some background, we speak about the decay, radioactive decay of two uranium isotopes. The green ones are the decay series of 238 uranium to finally 206 lead, stable lead. the yellow ones 235 uranium to 207 lead, and we ignore the decay of 232 thorium because it's not really used in ID-TIMS dating. Then a slide on the workflow of chemical abrasion ID-TIMS dating. So first we have to prepare our samples, crush the samples, separate the minerals, and this ends up with optically selecting grains which seem to us the best suitable. So it is very subjective personal choice. Then these grains, they get mounted into an epoxy mount, polished down to half, where we have the possibility also already to carry out the first in situ analysis, the trace elements, oxygen, hafnium isotopes, whatever we would like to do. And then we pluck the most suitable of these grains out and chemically abrade them. So chemical abrasion, I will go into more detail in the following slides, what this is, why we have to do this. We add a tracer, dissolve the zircon, separate uranium and lead, where the fraction we use for the high precision TIMS dating. Then we also have a so-called trace element fraction we can again use to have chemical information, trace element ratios at least, hafnium isotopes. So what is important here is the chemical abrasion process, and also the fact that we do isotope dilution. So isotope dilution is the chemical technique which allows for the most precise concentration analysis. And then TIMS as a precise isotope ratio measurement. The workflow for laser ablation ICPMS dating is very different. So we usually use a UV laser, like a 193 nanometer argon fluoride laser, which is directed onto our sample, which is the polished internal surface of the zircon, and then we ablate particles which get entrained by a flow of gas into the plasma through the interface into a mass spec. And this mass spec can be quadrupole ICPMS, can be a sector field, single collector, or multi-collector ICPMS. Just one word about precision and accuracy. So what we would like to have and what we hope to have is ID-TIMS dating. We have very precise, very accurate analysis. So they're in the middle. The average or the weighted mean age is equivalent to the true value. We, of course, don't know. So this would be the case, say, for one of the Earth time labs in the world who use a very well-calibrated Earth time tracer solution. And this could be another uranium lead lab which uses another tracer solution which is not calibrated against the Earth time solution. So it would be very precise but would be inaccurate. So the weighted average would be inaccurate. This could be the case of a laser ablation lab. So we have a larger individual errors, larger scatter, but the weighted mean age of this population of data would be still accurate at low precision. Whereas this lab here also has the same low precision, the same scatter, but the analysis, the weighted mean age is off. It's not accurate. And when we speak about precision, just to be clear that when we speak about ID-TIMS, we have about something like factor of 50 better precision than when we have in situ analysis, laser ablation ICPMS, or also SIMS. But precision, as you will see, hopefully very well in the rest of the talk, precision is not the problem. The problem is the accuracy. And of course, this difference in uncertainty, they are partly also derived from the fact that we analyze very different volumes. So I do not speak about SIMS dating in this talk, but with an ion probe pit, we analyze a few hundred of cubic micrometers of material, whereas with both laser ablation and also ID-TIMS dating, we are at the 10,000s of cubic micrometers. Okay. One word about the complexity of the system and how we can address this. So this is a Concordia diagram. 206 led to 38 uranium, 207 led to 35 uranium. This is the Concordia. So any point on this Concordia has exactly the same age for both of these decay systems. And now when we go and, for instance, we look at this zircon here, has maybe a core. The CL image has a growth zone around, has a second growth zone here, and then a margin which is much darker in cathodoluminescence, so it's probably high in uranium. So it's complex, but may possibly give us a nice age when we target the different zones with a laser. But you see these zones, I call this the white thickness. This is a term which came up in the last 2 years. So these are areas where we have dissolution reprecipitation processes, maybe recrystallization processes, and they give 2 young ages. So when I see a zircon like this, I just keep my fingers off. This will not yield a reliable age. So zircons have lost lead by any process. They will be on a discordia, which goes down to the age of overprint. So when it's happening, it will be 0. The moment the loss is happening, it will be 0. Whereas this grain here, this also has clear core and then several growth rims, epitactic, maybe also this high uranium rim, outermost rim here. This is clearly inherited. This is clearly magmatic. So such grains or analyses, they will lie on another discordia, which goes up to the age of the inheritance, which is here 514 million years. And this grain here shows very nicely 3 consecutive growth zones. Has been dated 588, 443, 276. But it also shows that these zones here, they are kind of blurred. There's also this whitish aspect. And since I know the geological history, I know what I should get, I can tell you that these ages are too young. So also here, when I see these blurred, not clear oscillatory zonation, I know that this zircon has already undergone some secondary alteration. And I would like to avoid such a grain for laser ablation dating. And of course also for ID-TIMS dating. So now we go into a bit more detail for these 2 techniques. So first, the chemical abrasion ID-TIMS geochronology. So the first thing we have to do is to select the best grains, best. What does this mean? So when I look at this is a random collection of some grains I found on my computer. So this one looks actually quite okay. It's transparent, this one too. I will take these probably, but I will definitely not take this one. Is dark, has an inclusion. This one is also dark, has some black inclusion here. This one the same. So this is already a first very subjective selection I have to do. And then we have to do the chemical abrasion, which I will just come back in a second. Or we do the first step of the chemical abrasion, which is the thermal annealing. Then we mount the zircon, we do the CL imaging, and then we pluck out the most suitable grains, which show no cores, which show none of these fluid alteration phenomena to continue with the ID-TIMS dating. But before I can go further, I think I have to comment on the fact that the alpha decay damage is leading to the biggest problem, which is the lead loss. So for this, we apply what we call chemical abrasion. So what is the reason? So we have the decay of our parent nuclide, 238 uranium, it ejects alpha particle, which is a helium, a 4 helium, which is traveling at some distance through the lattice and does some damage to the lattice. But actually the recoil of the first daughter nuclide, which is the 234 thorium in this decay series, is traveling not too far, but makes a much higher degree of damage to the lattice. And this damage can be quantified or related between the radiation dose. So this is the number of alpha decays per unit. So in units here of 10 to the 18 alpha decay events per gram. And this is, on this axis, the degree of ordering. So 0 would be fully ordered zircon, 1 would be fully amorphous zircon. And we see that the natural zircon here from Sri Lanka is aligning along a curve and arrives at something like 7 or 8 times 10 to the 18 alpha decay events per gram, arrives at the fully amorphous state. So what we would like to have for our ID-TIMS age determinations, we would like to have zircons which are below something like 3 × 10⁻¹8 alpha decay events per gram, which are so-called at the first percolation point. Whereas these grains here are called to be at the second percolation point. This is really strange. Okay. So for this, we have to apply this chemical abrasion. So it consists of 2 steps. First step is the annealing, 950 degrees, 48 hours. So this is actually to anneal, to repair the parts of the grains which are at the first percolation point. So smaller, with a damage less than 3 × 10⁻18 alpha decays per gram. And then we want to get rid of the rest, because we know that the rest has undergone a higher degree of damage and is potentially has lost part of its radiogenic lead. So we do this using exactly the same acids we use for complete dissolution afterwards, just a bit shorter time. Same temperature, but shorter time. So this solution will happen in something like 2 to 3 days. And our partial dissolution step is 12 hours, 10 to 12 hours. By doing this, we hope to get rid of all the domains in the grain which are at the second percolation point, and we are left with a grain which is a skeleton consisting only of repaired domains of the zircons at the first percolation point. And we can actually calibrate this or control this by doing micro-Raman spectroscopy. So this is a diagram showing the wave number of the Raman bands, the Raman shift, versus the full width at half maximum, so the shape of the peak. Pristine zircon would be at 2008 and have a very narrow peak. And then the radiation damage trend would go in this direction down here. And what we do, we anneal them, so we go back in this process, but more importantly, we dissolve the more damaged grains away. So what Wiedmann et al. In 2019, what they proposed is a kind of area of confidence. When we are back here with our chemically abraded zircon, we can be rather sure that we do not have any more alpha decay related lead loss. And then another word to the precision. So the magic term here is the radiogenic to common ratio of lead in analysis. So this is a diagram. Here is the percentage of the uncertainty of our age we get. So 0 to 100%, which is plotted against the zircon radiogenic to common ratio. And we see that there is this limit around 15 or up to 20 maybe. When we have radiogenic to common ratios which are smaller than 15, the uncertainty is dominated by the uncertainty on the isotopic composition of our blank, so our common lead. We think that there is no common lead in zircon mostly. The lead has no space in the zircon lattice. But it's actually what we find as common lead in our analysis is what we have added through the procedural blank. And when this is the case at these lower radiogenic to common ratios, it's sufficient to use a single lead, 205 lead, a double uranium isotope tracer. And we can only improve the situation by having a better control on our blank isotope composition, that we have smaller uncertainties on this composition we use, or we can reduce the blank, that we get to higher radiogenic to common ratios. And above this value here, actually this source of error gets less and less important, but the error is dominated by the fractionation. So the isotope fractionation, which happens in the mass spec. And for such analysis, these are analyses at high radiogenic to common ratios. We use the doubles tracer solution, 202 lead, 205 lead, 233 uranium, 235 uranium, which can be, so the double spec can be perfectly used to correct online for the fractionation. And then a question which always comes, of course, how reproducible are the best ID-TIMS labs worldwide? And this is now easy to answer because there is a paper now in review of the Earth-TIME consortium. So we produced a zircon solution from Pleschowitz, thousands of Pleschowitz grains which have been dissolved and then spiked with a single lead double uranium spike. The reason why we only used one single isotope of lead is that we have not enough tracer solution with the double lead isotopes. And we sent this out to a certain number of labs, and most of the labs got back with results. And amazingly, so 120 analyses from these labs, they align along a 206-238H, which is highly precise at the value which is certified. And actually the scatter of this whole population is within analytical scatter. It's just still acceptable at the MSWD value of 1.5. However, when we plot the weighted means of each lab, it's clear that we have excess scatter. But nevertheless, even if we take this excess scatter into account, we get to a standard deviation, standard deviation of 0.05 of the 206-238 uranium date. So that means, in other words, that any scatter from ID-TIMS states, which is beyond, so a set of scattering dates, any scatter which is beyond this 0.05% of the 206-238H is natural. But of course, don't forget, these are analytically perfect measurements at very high to very high radiogenic to common ratios, and natural zircons are sometimes much less ideal. So natural cause, this could be protracted growth, this could be anticrystic or xenocrystic contributions, or also dissolutionary precipitation, which are rendering our grain younger. So our wonderful analytical performance gets, of course, then destroyed by these natural complexities. One word for the presentation. So we have abandoned the 235 uranium to 237 lead decay, at least for Phanerozoic ages. Why? So look at this green ellipse here. So this is a measurement, a real measurement we have done, and it has been corrected for the procedural blank with our average of the blank composition we have in our lab in Geneva. But of course, this is a series of measurements, so we have to add an uncertainty to these values. And when we now shift this ellipse within these uncertainties, we can make it easily inversely discordant or normally discordant. That means the 207 to 35H is actually not significant anymore. It could be 250 or it could be 253. That means we abandon this H. We only use the 206 to 38 uranium H, which is the most solid and robust estimate for the H. At least this is the case for Phanerozoic ages, and it's very important that you never ever think of reporting and using the Concordia age. You have to be careful in isoplot or isoplot R to deselect the Concordia age, because what would be the Concordia age? This would be the average of this age here and of this age, so it would be completely false. And for Precambrian ages, of course, we can make the limit at 600 or 1000 or 1300 million years, but at Precambrian ages we use the 7.6H. Okay. The main challenge for ID-TIMS dating is, of course, that we should never forget, this is a bulk analysis. So we are analyzing a whole grain, despite the fact that we clearly see in this grain 4 distinct growth episodes of this zircon. So this is a core, which is not an inherited core. It's a core which anticrystic core, which crystallized a few 100,000 years before in a deeper level of the same magmatic system, got this resorbed, and then overgrown by zone 2, overgrown by zone 3. The two are again separated by a rounded resorption surface, which is truncating the zoning of 2. And then there is a late overgrowth, which is probably high uranium because it's dark in Cl, which is zone 4. So we cannot resolve this. There is no in situ technique which would be able to resolve a few 100,000 years of zircon growth at a Milner at 36 million years. But what we can hope is that when we analyze now 30 zircon grains from this sample, that we find by pure coincidence, maybe one grain was only grown during the phase one during phase 2, phase 3, phase 4. So we do not only find these highly zoned zircons, but maybe zircons which are entirely formed by one of these 4 growth zones. We can hope, at least we can approximate the total scatter to this mixing process. And this is a real case. This is published in Samperton et al. 2015. This is the Bergell granodiorite. So something like, I didn't count it, but 30 analysis maybe. So how should we now, in a real case, interpret this? Because finally, we would like to be able to answer the question, what is the age of the Bergell granodiorite? So should we use TÜV-ZIRC or some other of these approaches just to kick out the oldest, the youngest, the oldest, the youngest, then we finish with an intermediate cluster at the precise age and the population with a MSWD, which is statistically significant. I think this is clear to everybody. This is not scientifically sound. This is a virtual precision. We could also say, okay, these are all anticrysts. They crystallized in deeper levels, at deeper levels of the system. Only the youngest one crystallize close to the solidus and gives us the age of the emplacement, maybe, of the whole magma. Maybe, but maybe it is also influenced by lead loss. We could also say, okay, no, let's be democratic. All of them crystallized in the magma we see today, or we encounter today as a granodiorite. So this would mean granodiorite is up in the uppermost crust, is actually intruding into nearly non-metamorphic sediments, but had melt present during 650,000 years is thermally impossible. So we find some nice Swiss compromise. There is some anticrystic part, and then zircons which kind of reflect a protracted growth, and probably the last one, probably still a grain where we didn't manage to get rid of the lead loss. But it's an interpretation and is purely subjective. So the fact that we have these anticrysts here means, in other words, that zircon is actually happily floating in the magma for quite a long time. So when we look at these data from the Fish Canyon Tuff, Watzlaw et al. 2013, via some modeling, fractional crystallization, he came up with this model that there was a magma which contained maybe something like 40% crystals only, but then solidified over 200,000 years while it was crystallizing zircon, was nearly solidified at 76% of crystals, and then happened something. Either there's a hot magma coming in or isotherms were moving, but then the magma got rejuvenating, zircon got continued to be saturated, so crystallizing, but the crystallinity of the magma dropped again back to 40–45% of crystals and then exploded. So that means when we take a hand specimen of the Fish Canyon Tuff, we have most of the grains we will encounter will be anticrysts and not dating dating or close to the age of eruption. And that is easiest is to, of course, to show this using lavas from the Mount St. Helens, because we know exactly when this erupted. And any lava, you take a sample, you separate the zircons, you see that the sample contains zircons up to 600,000 years older than the eruption age. So this could be anticrystic zircon, which just got recycled in the magmatic system. But don't forget that there's also the possibility that there's some really very small core in the center, because zircon has to nucleate from something. And so there could be a nano inclusion of an inherited core, which moves your analysis slightly, but definitely would not move sufficiently that it would leave the concordia. So they stay analytically concordant. Okay, this was some things about ID-TIMS dating. And now, laser ablation ICPMS geochronology. So the first comment is that the CL imaging, cathodoluminescence imaging, is really essential. And my message here would be that first, separate your zircon, image them carefully at high resolution, make your mind up about the crystallization history, and then shoot. Then shoot into zone 1, zone 4, zone 5, after you have defined these growth zones. So 1 would be an old core, is present here, is present here. 2 would be a growth zone, sector and oscillatory zone. Sometimes there's no old core, and sometimes this zone is also outside at the outermost rim. So later on, I realized that actually 3 and 2 is the same. And then the whole thing is overgrown by a zone 4, which has a low luminescence, so high uranium. Sometimes 2 and 3 are lacking. So this is directly overgrowing 1. And 5 would be any sign of any overprint, blurring, non-planar, planar, wavy zones. So this is, for instance, a core or a growth zone 2 actually rather, which is completely altered by secondary effects. Here we see this secondary rim. Here we see also probably a recrystallized rim. And only then target these zones separately, and then establish your set of analyses from the zone 2, and then only calculate the age from those analyses which are in the same zone. Then the other thing, which is a very clear difference to ID-TIMS, we need external standard for a laser ablation ICPMH. In the ID-TIMS, this is our spike, our tracer solution. Here we have this external standard. So actually, why do we need a standard? Actually, we need 2. The primary standard we need because we take our primary standard, we shoot with our laser on our grain. We know very well the age from ID-TIMS dating. And then we realize that actually the intensity ratio 206 to 35 is not equivalent to the age we should get. We have fractionation in the laser spot during the transfer and then also in the mass spectrometry. So the concentration ratio, which gives us the age, is not equivalent to the intensity ratio we measure. So we have to establish this correction factor, beta, which is called the relative sensitivity factor. It is calculated from this equation. And then we apply this to another sample. So first, we have to control whether our beta is really correct. So we use a secondary standard, from which we also have a very precise and accurate ID-TIMS age. We do the same exercise, but here now we assume that the beta is the same. We just apply this. And very unfortunately, there is some problem with this. The first problem is that the beta is varying within a day or also from day to day, depending on machine parameters and also fluctuations during the day. So what we need is to have a representative day-to-day statistics of beta obtained on our secondary standard. And that means that from this equation, we can calculate the variance. So the variance in our intensity ratio normalized by the beta is equivalent to our variance in age. And this variance is also applicable to our unknowns. That means this variance has to be propagated onto our unknowns. And just to show you that this is not a fairy tale, these are own data from the laser ablation lab of the University of Lausanne. So Alexei Ulyanov is the head of the lab. 4 sessions I did over 6 months. The maximum dispersion, so between the oldest here and the youngest here, is something like 3 million years. This is already a percent of the Pleschowitz age, which is at 337.2. And some of the ages are inaccurate. This one is too old, this one is too young. So that means we have to propagate these uncertainties to our unknowns, because these unknowns here are too young. This day I measured them, they will be too young, these will be too old. And what we do in Lausanne, we have a running mean, or Alexei has a running mean of 12 months, where he does statistics on 12 months Pleschowitz measurements from anybody who is using the lab, and he comes at something like 1.6% of two standard deviations. And this uncertainty we now have to propagate on our total uncertainty in this way. So the best is that we report 2 errors when we give a laser ablation age. The internal one from data scatter alone, and then the integrated one, the long-term, adding the long-term uncertainty calculated in this way. What is the reason for this relative sensitivity factor? This is the matrix. So the zircon is not only zirconium, silica, and oxygen. It has a lot of trace elements which replace zircon. And on the zircon side, but also can replace silicon on the silicon side. And there is a series of elements. I have no clue where they are. And then in addition is the radiation damage. So that means any natural zircon is heterogeneous, has a natural variation of trace elements. And the variable decay damage actually leads to a variable ablation efficiency. So this is actually the easiest not to overcome, but to improve. When we anneal our zircons at dry in a furnace at 950 degrees, we get rid of part of this analytical scatter due to variable ablation efficiency due to radiation damage. So if we want to quantify this matrix effect, we can do empirical round robin exercises. So one I'm aware of is Klötzli et al. 2009. So they took 5 reference zircons. You take the first one as primary standard, and you measure the 4 other ones as unknowns, and then you go to 2, 3, 4 all around. And the surprise, of course, the beta of the first is not equal to the second, third, fourth, and fifth. And they report several % of dispersion among these 5 reference zircons they use, several %. So what is the conclusion out of this? So no single analytical chemist in the world would rely on a 1-point calibration for element concentration analysis. You know, XY, you have at least 3 points, you make your calibration curve. But we think that with 1 it's fine. So realistically speaking, our accuracy is definitely not better than 1.6%, but could even be worse. So is maybe chemical abrasion the solution to this problem? At least the lead loss we could mitigate through the chemical abrasion, because most labs, or 99% of the labs, they measure untreated zircons for laser ablation, ICPMS dating. And the consequence is that these states always show a large scatter and always have this young tail which goes down to young ages or to young ages. And there are several studies, but this one maybe is the most complete, of Vonquat et al. 2014, they have measured from a series of rocks established a good data set of non-chemically abraded zircon, green, and then chemically abraded zircon from the same sample in red. So what do we see? Chemical abrasion clearly reduces the total scatter, and it also removes this part, at least, of this young tail, which goes down to younger and younger ages. And when we take now this example, this rock sample here, as representative, we can say there is no doubt that in a rock of 20 million years, there is significant amount of lead loss. And what the people now do, this is another example of older, around 300 million years. So of course we take this array of data, we make a weighted mean age. Even so, we actually, statistically speaking, we will not be allowed. There is excess scatter. And so the difference between the weighted mean age of the red and the green in this case would probably be several %. So Vonquat et al., they give a range of 0.9 up to 4 to 6% as a difference between the 2 weighted means, chemically abraded versus non-abraded. And there is quite a bit of statistical modeling done, and which is nice, but in a way, a statistical treatment of bad data is not what brings us away from this difficult situation. What what we should do is try to improve the boundary conditions, and actually doing thermal annealing of all grains we analyze afterwards for laser ablation uranium lead dating is a minimum effort and would probably remove some of this scatter. But I'm not aware of any really significant study. Which now leads us to some case studies where we can compare the two techniques. So this is a porphyry copper deposit, nice laser ablation cluster, weighted mean age. And then these zircons where we have these circles, these were plucked out of the epoxy and dated by chemical abrasion ID-TIMS dating. And what we now can see that this cluster here, which is actually analytically even, statistically even significant, is inaccurate. It's too old because the chemical abrasion ID-TIMS date is younger. So from this, and it's too old, but when we take now into account the external reproducibility, again, the 1.6% external error, then we get to overlap. So what we can take here as message is that the laser ablation date is too precise, is inaccurate, and too old. And what we definitely, concluding from this, what we should never do is to take the oldest and the youngest of the laser ablation spot dates to calculate the duration of zircon growth. I have seen this in some papers. This is of course forbidden because this is analytical scatter. Another example going the same direction, also a porphyry deposit. We have laser ablation dates from these late P3 porphyries. So from the same lab, from the same author, two sets of data, one large scatter, some excess scatter. Yes, a bit of excess scatter, but still accurate. And the second try was a huge scatter, and whatever average you take here is too young. And we know this because there is also chemical abrasion ID-TIMS date here. And from the same lab, for the P2 porphyries, we have a statistically relevant data cluster, which is too old, because we also have here chemical abrasion ID-TIMS dates. My point here is that the duration which was calculated from the laser ablation dates, the duration of magmatism, is completely off, is an artifact of these analytical problems. The duration is probably something like 160,000 years and not 1.4 million years. So in generally speaking, laser ablation dates are not suitable to accurately estimate the duration of a geological process. But now, it's also very negative, very pessimistic. So how to treat then data sets with excess scatter? So this is an example. All zircons are untreated. All analyses are nicely concordant. This is a Miocene sandstone in northern Italy. We know that the zircon detritus is coming from the Adamello bathylis, which is around 37, 38 million years old. It has a lot of excess scatter. So we can ask three questions. What are the explanations for the excess scatter? Question 2, how old is the Adamello bathylis? Question 3, what is the maximum depositional age of this sandstone? So question 1 is easy. Lead loss. These are untreated, so the youngest grain, definitely these clustered, they are biased by lead loss. We have some scattered towards older ages, maybe we have dissolutionary precipitation processes, some anticrystic, xenocrystic component, which produces this tail maybe to higher ages. And in addition, the overall analytical scatter, which we have to add. So this question is rather easy to be answered in a qualitative way. Then, how old is the Adamello bathylis? There are three approaches. The young single grain date is absolutely forbidden. This is for 100% sure lead loss. The youngest statistically valid population of at least 3. Even so, this is kind of the agreed procedure in detrital zircon. I think in this case, I would be very careful. I would assume this is still biased by a lot of lead loss. Then what we could do, we do kernel density estimate curve. We take the mode and we say, okay, the youngest mode of the kernel density estimate curve is giving our age. This would be around here. So what we do, we mix together two natural phenomena, lead loss, memory to some older components, and plus together with an analytical scatter, and call this then a best estimate for the age. So for me, personally speaking, this is an absolute no-go. We are not allowed to do this because we are mixing together sources of error of very different nature. So what can we do to improve the situation? We can do ID-TIMS, or at least we can relate each single spot to either the growth textures, as I showed you before, or maybe we analyze also some trace elements that we have some chemical composition, so petrochronology. Then we have the third question. What is now the maximum depositional age of this sandstone? So again, youngest grain is forbidden, youngest cluster probably also biased by lead loss. Again, the youngest mode of the kernel density estimate, the youngest mode, I find is a no-go. And I even find this in a case where it overlaps with the ID-TIMS state. Maybe the ID-TIMS makes the same mistake, that we mix together very different error components and we create an artificial kernel density mode. So now I cheated a bit. This is not the real case. This is a fake case. These are 4 separate intrusive bodies in the Adamello-bacillus, partly, not all, but partly with clearly cross-cutting relationships. That means, in other words, that the laser ablation data we have assembled here, they completely fail to describe the structure of the data set. If we did trace element analysis on the same spots we have used for dating, we would realize that actually the trace element characteristics of the zircon of these 4 intrusive bodies would be slightly different. So this could help. So this would help us. In other words, laser ablation ICPM dating cannot resolve time beyond its inherent imprecision and inaccuracy, which is at least 1.6%. And the last example, Neoproterozoic granite in Brazil. Any sample you take from this granite is a huge granitic body. Shows at least 40 million years of age range in one single sample. This was interpreted as an example of a hot origin, 40 million years of presence of melt in the deep crust. But then you take out some grains, do chemical abrasion ID-TIMS, 581.35 plus minus 0.16 million years. So this age dispersion here is again an artifact of a complex history, which is mixing together different geological growth events together with lead loss. These are untreated zircons. So laser ablation ICPMS dating are too imprecise to resolve the complex geological history here. So, as a very last example, I can show you an example now where laser ablation ICPMS states can even form clusters, which are artifacts. That means a cluster of points does not represent the growth age. So this is an example from the Transvaal supergroup, published by Sänger et al. 2023. So Martin is present here. So there is a problem between correlating the Makanyene formation, is a glaciogenic formation in the equivalent west basin, so in the west of a huge basin, and the Heckboard formation, which is in the eastern part, East Transvaal basin. So this correlation was problematic, and these 2 units, they were correlated because the Heckboard shows a clear mode of ages at this age here, and the Makanyene formation shows these clusters at 2.23 billion years, which then allowed people to correlate the Makanyene formation with the Heckboard. But now what Sänger et al. Did, they took out the youngest of these grains from this mount, rotated grains, did chemical abrasion, and this 2.23 billion year old cluster disappeared. What does this mean? Now suddenly there is no more attempt to correlate the Makanyene formation with the Heckboard, but it's correlated in age with the other formations of the East Transvaal basin. And so by doing this, the maximum depositional age of the Mach-Ganyena formation is getting older by 200 million years and solves quite a bit of east-west correlation problems. Okay, so what can we conclude from all this? So first, I would like to put up 4 take-home messages. So I think high-quality CL images to establish a growth history are essential, not only for laser ablation dating, also for ID-TIMS dating. And high quality, I mean not having as many grains on one image as possible, but having CL images where you can distinguish the individual growth zones and come up with a growth history. Overestimation of the precision of laser ablation ICPMS dates. So the accuracy is not better than this value. So any precision which is derived from adding more and more of data and then making a standard error of the mean is not helping. You get further and further away with your accuracy. You cannot derive durations nor rates from laser ablation ICPMS dates, I think in a very general sense, and people who are using a lot of laser ablation dating, which then gets controlled by ID-TIMS, they again and again realize that this is a sentence which is bloody true. And from the other method that so any scatter of chemical abrasion ID-TIMS dates beyond 0.05% of the 206 to 38 age is not analytical but natural. So I could stop here, but I was told that it's very depressive for the people who are using laser ablation dating, and these are about 99% of all dates which get published. So when we now think, how could we improve or develop laser ablation ICPMS uranium lead dating? Maybe at one day we may arrive at multiple standard calibration procedures. So not having one primary standard, but 5 or 8. But I think this is time-wise, and this is impossible. Maybe it's possible with automatic devices one day. What we could do, at least consistent application of thermal annealing to reduce this variation here. This could be done easily. And we should undertake more efforts to systematically evaluate how chemical abrasion could be adapted to laser ablation dating. It cannot just be used in the same way as we use it for ID-TIMS, because when we chemically abrade the zircons, they are very fragile afterwards. We have to put them into an epoxy mount afterwards and polish them. So this is a nightmare from the manipulation, but maybe there is a way how to adapt it. We should use much more Raman spectroscopy to quantify the degree of alpha decay before we analyze the grains. The easiest is destruction-free. In most departments, there is such a Raman spectroscope standing around. And we should probably use supplementary information to trace elements. So what we call petrochronology, maybe we can use trace elements or trace element ratios to establish something like an offline calibration or an offline normalization, as we do for strontium isotopes, neodymium isotopes, where we do the fractionation correction online in the mass spec, but afterwards we calibrate externally for a systematic offset from standard. And I was strongly advised that to from time to time check some of your laser ablation ICPMS dates with a few chemical abrasion ID-TIMS analysis to have an idea of the inaccuracy you're dealing with. So that's it. I have, because it will be accessible afterwards, I put together a collection of references I mentioned in the talk. Not all, but it's a selection. Thank you very much for your attention.
Huge thanks, Urs. That was really great.
Yeah.
We're going to switch to question and discussion. So you can ask your question by either typing it into the chat or finding the raise hand button at the bottom of your screen. You can hover over or click reactions, and then raise hand button shows up right there. So we'll give a little bit of time for people to formulate their questions. So, Urs, I guess I can start with a question, but my question might be a little bit, because I don't do much zircon work really. I might be a little bit naive, but I'm picturing in my head these big data sets from people who just analyze thousands of zircons for detrital zircon studies, and it seems like, I mean, what would your response to, like, maybe or the fact that this takes a whole lot of time and resources to do such detailed, checking of every single grain for growth zones? What would you suggest to this extent, that someone trying to approach a question like this, what should they keep in mind?
Yeah. So you speak about the detrital zircons, huh?
That's right.
Where we deal with large large numbers of grains. So of course, what the people do, they remove first. They use the degrees of the discordancy argument. So they remove analyses which are discordant, and then they do statistics on the dates. And I mean, you just should not forget that when you have a peak, a peak in your age distribution, you assume that this peak is equivalent to an event, which is reflecting an event in the provenance area of your sediment. You just have to be aware that, of course, the width of the peak is maybe a range in ages, but it's maybe also a statistical, so an analytical variation. And I think for this, I would say for this application, I would probably not go further. There's no way that you can do any further pre-treatment before analysis. I think the problem is arising much more when you want to interpret your detrital zircon information in terms of maximum depositional age, and I think this is the most dangerous thing. At least there where you think you are close to the real depositional age.
Got it. All right, thanks. Greg Ritalik, please go ahead.
Yeah, that was great, Urs. Mark Schmitz did both methods for me recently in the Purba, and it was really handy to be able to sort out the relative merits of the two approaches. But I'm actually asking about the Makengeni gate, because I've been long fascinated by the paleosol in the Heckport. Now, my main question is, what did you analyze in the Makengeni? And then the second question is, the Heckport is still about 2.2, right? Not 2.4. Yeah, what was the was it a volcanic rock or was it a sandstone in the Makengeni?
So it's not a sandstone, it's this glaciogenic, the tillite, but the zircons are detrital, right?
Oh, so these are detritus. Yes.
Yes, these are detrital zircons, yeah.
Very
Yes.
good.
Yes. So I have to remove the.
And this doesn't affect the date of the Heckport at all,
No,
right?
no. We did not work on the Heckport. So that the Heckport age is kind of defined by this peak here. So this is younger than the other units in the East Transvaal Basin, but this is the age of the. So this is the age of this younger cluster. I mean,
Sweet.
these were several points, right? These were not just one. And
Right.
Can I add something
yeah.
concerning this question?
Yeah,
So we did date the Heckport, and the age hasn't changed. Answering your question,
Yeah,
the one that we did see, we did observe a change, that was the disappearance of all these young cluster that are being shown in this slide. Are all the detrital analyses that were simply overly young for the Makengeni formation, and we did like a multi-step chemical abrasion procedure, which means instead of doing just 12 hours all at once, we did 3 hours first, then we added more hours, and this cluster disappeared within the first 3 hours. So they were highly metamic zircon crystals, and that's the explanation we used to explain why they were so young.
Yeah.
Sweet, thank you.
But
Thanks, Martin.
just a comment to Greg's question. The age for Heckpert is still not well established, but it's certainly younger than 2250, 2260. So it's not correlative to Maganini, but we still don't have a precise age for Heckpert.
All right, we had one from Bodo Weber. How do you determine the grade of order in the zircons you presented? Is this by Raman too, or do you use EBSD?
No. It is what you can do a lot of analytical work. It's always a question of what is reasonable within the time frame. So what is easy and fast and destruction free is Raman spectroscopy. So you can use the deviation of the 2008 band and the full width of maximum to get an idea of the disorder, using this correlation between amorphous fraction and alpha dose. But of course, you could do a lot of other approaches, use other approaches to quantify the degree of disorder. Yes, totally agree. But I think it's not feasible because finally you want to get an age.
Okay, next in the chat, we also have a question from someone named John. Thanks for a great talk. You brought up the point that zircons, like all minerals, start from some nucleus. Is it homogeneous nucleation wherein the zircons must start from a previous zircon nucleus, or can they start homogeneously and therefore not have a xenocristic nucleus?
Yeah. So thanks for this question, Jahan. I wish I could answer to this. This was a discussion point among many beers already between people in Lausanne and in Geneva and me. I think that they are, so let's say that there's certainly some zircons probably nucleate spontaneously. So you would have to calculate the energies which are needed, undercooling or oversaturation, that this really starts from a cluster of 5 ZrSCO4 molecules. But I would also fear if you go and really look in very greatest detail, you'll find nanoxenocristic cores in many zircons. And I would say this is a source maybe of some age scatter. We are maybe capable of resolving with high precision dating, but we haven't thought about this in detail. So zircons who grow concentrically from an innermost core, they would be nice to go there and have a detailed look at this smallest core. But of course, you need to be able to polish down your zircon to exactly this level, which is also just coincidence when you manage. But I cannot give you an answer. I would like to know.
Okay, next, Don Davis, please go ahead.
Urs, great talk, fantastic slides. I had just a few comments to make. Actually, in response to the last question, the nucleation of zircon, I think in order to explain the presence of oscillatory zoning, which is particularly present in felsic zircon from felsic rocks, you have to see a process in which the zircon supercools in the magma until the concentration becomes high enough around it that it spontaneously starts to precipitate around the zircon. And in that case, uranium will come in, a lot of uranium, because zircon has a very high partition coefficient for uranium, and then it will trail off because the zirconium has a faster diffusion rate than the uranium. So then it grows to a certain extent where it becomes saturated again and then supercools and then becomes another step of growth. So that probably explains oscillatory zoning. So it may need an initial zircon seed to start, but from then on, it will continue to sort of grow in spurts like that. Anyway, a couple of other comments. One is, you remember that Tom Crow pointed out many years ago that the reason why zircon becomes disturbed is because of alteration, not because of radiation damage. You can have a perfectly metamorphic zircon, which gives you a concordant age, basically. So whereas the CL method is designed to remove zircon that's damaged. So it removes not only the alteration, but the radiation damage parts. And I found that to my dismay once when I had beautiful high uranium zircons from a gabbro that I tried in my early stages of using chemical abrasion. And of course, after a couple of hours, they totally disappeared and I was left with nothing. And another problem is with Archean oscillatory zone zircon. Then you have high uranium layers, which may be only microns in thickness that are separated from low uranium layers. And when you do chemical abrasion, what you get is a comb-like texture where the low uranium layers have survived, the high uranium layers have been washed out. And when you analyze it, you find a point that's slightly above concordia and too young, because uranium, radiogenic lead from the high uranium ones has been recoiled into the low uranium ones. And because the average recoil distance is longer for 206 than it is for 238 than for 235, then the age is slightly too young. So there can be problems there. But I would like to emphasize the importance of using BSE imaging, especially for old zircons, because alteration under BSE, which is what you're trying to avoid, is dark, whereas the high uranium parts, which host the alteration, are bright. Whereas it's the opposite with, as you know, with CL. And in places like China, they do exclusively CL, no BSE whatsoever. So if you have an old zircon, you really can't distinguish the alteration from the high uranium areas. So I like to look at, well, preferably BSE, but ideally both. Anyway, the other thing is laser ablation ICPMS. Of course, there's a huge difference between a lead over uranium age, which you have to use on Phanerozoic zircons, as you pointed out, and a lead age, which you use on Precambrian rocks. So there's no isotopic fractionation between the 207 and 206. So that those ages should be much more accurate than ages based on 206 over 238. So you talked a lot about standards and stuff like that. But the problem with 206 over 238 is that the ratio isn't constant during the analysis. It goes up basically and sort of levels off the longer you analyze over, say, a 30-second analysis. So exactly which value of 206 over 238 do you pick?
Yes, of course. The first approximation is that you correct for this downhole fractionation. I mean, that's still part of the analysis, so there are different.
Yeah, how do you do that exactly?
Yeah, well, there are linear, there are very different approaches. Yeah, which actually I cannot even not tell you now what we are using in Lausanne.
Yeah, because Gerald's uses the last part. Basically, it tends to form a straight line, and increasing ratios increase after the first 10 or 20 seconds, and he uses that and then projects down to time zero. But then again, that's
our low curve, and so I don't know. I don't know exactly how.
Anyway, this all occurs because you're getting lead is highly volatile, of course. So when you ablate the sample, you form an ablation cloud, and you separate the lead from the uranium, and the uranium condenses in the melt globules, and those go right into the ICPMS. Whereas if any material becomes trapped in against the walls of the pit or around it due to fallback, that will be essentially depleted in lead, but contain uranium. So of course the excess lead goes into the signal, and that's why it continuously grows. I've been trying to model this for about a year now, and it's really complicated. And it's tearing my hair out trying to figure out exactly, what is the best way to calibrate this. But in any case, in terms of, I think personally only a fool would try to use LA-ICPMS to date Phanerozoic rocks because it's so difficult, potentially inaccurate. But for my experience in Archean and Proterozoic rocks is that it's really, really useful because you can use almost any zircon, basically. The trouble with ID-TIMS is that you have to go through the whole population of thousands of grains very carefully and pick out what you think are the best grains, which are highly unrepresentative or could be of the main population, of course. Whereas even if you have a grain that's totally cracked up, as long as you have, you know, a 20 micron size domains within there, which are not damaged, then you can apply the LA-ICPMS. So,
of course, there are the many
yeah.
questions. I could give many answers. Of course, my talk is mainly focused on the Phanerozoic rocks. It was clear.
Yes, yes, yeah.
Cambrian rocks.
Mhm.
So this, but I would assume, you know, all what actually the whole story I told was after the correct fractionation correction. You know, this is done. This you are completely right. Of course, you have to correct accurately for the downhole fractionation, but this is not I'm not specialist of the machine part of laser ablation dating. I'm a user, huh?
Sure.
And we are mainly I would say most of the laser ablation age determinations are done on the Phanerozoic rocks and not on old rocks, because I don't know how many thousand, I would say there are many thousand analyses done every year on porphyry copper deposit rocks by all the companies, and they shoot hundreds and hundreds per day, Phanerozoic without any pre-treatment, and they exactly face all these problems of what I was talking about. Of course, you are totally right that the processes in the laser pit have to be understood, and in the mass spec also, of course, the fractionation in the transfer zone, they have to be modeled correctly, corrected correctly, yeah, accurately.
Okay. Anyway, great talk.
Thanks.
Okay, great. I don't see any more questions or hands up at the moment. I'll leave a few seconds though.
Yeah, maybe ask a couple of questions. So Urs, for like many applications, well, at least more relevant to us, is defining a depositional age or maximum depositional age. And it seems like you explore some of ways to calculate maximum depositional age, and kind of at least 3 of them you have doubt about. Do you have any recommendation or thoughts, like what would be maximum, what would be a best way to approach maximum depositional age? Obviously, if you get something with questionable from geological constraints, you should go to TIMS, but it's probably not realistic to go in all cases.
Yeah, so of course it would be probably the best would be just to, you know, to do your laser ablation study on at least on annealed grains, and then take the youngest, which you think would be the ones who define the maximum depositional age, and analyze 2, 3, 4 by ID-TIMS. This would mean that you must have an ID-TIMS lab at hand who is able to do this. And of course, I see that this is not always possible, and that's why I think to develop or to adapt chemical abrasion to the laser ablation dating, this could be a way out. I think this would be possible. Not one-to-one, not that we just use exactly the same procedure, because the zircons maybe get too fragile, that they can be afterwards embedded in epoxy and polished. But I would, so generally speaking, I would say that uranium leadate, especially on an old zircon, which is not chemically abraded, is not reliable. So let's maybe focus our attention to develop a technique of chemical abrasion, which is still useful and not too much time consuming for laser ablation dating.
Thanks. And maybe second questions both to you and Don, with respect to discussion on sort of what laser ablation is not perfect for Phanerozoic zircons. So we, in our work and with Maria, like we run into situation with the latest current zircons. We kind of run in a situation that we give like early Cambrian ages, and it seems like we several times run in this situation, and maybe the situation is less common when you go to old ages, to older zircons. So where would you put kind of like a time boundary where you should be particularly concerned about using laser ablation? Time boundary in terms of ages of zircons.
Well, I mean, one aspect that Don mentioned is clear that as soon as when you switch over to 7.6Hs, you don't fractionate 7 to 6 So you still have the problems that you have the lead loss, but I would say
800 million years, maybe it's something like that.
Yeah, but however, you always assume when you have this so concordant and then slightly discordant array of points, you always assume that that is okay to take the 7.6H because it's lead loss, so it's diffusional lead loss. But actually, when you mix this with geological events which were 100, 200, 300 million years after the initial deposition, so metamorphic events, then you make also a mixture of several H components, and this you cannot resolve with laser in any case, because your analytical uncertainty is just too big. Maybe the 7.6H is more reliable, but you still make some, I think, fundamental and systematic errors with the interpretation in such a case. And there's not a way out, we cannot tell everybody now we have just to forget about laser dating to ID-TIMS. I don't know how many 10,000s of spots are analyzed every year on this planet. So not possible.
And after 1 billion years, 7:6 ratio, you cannot push it to use it for younger zircons after 1 billion years. Is it just a problem with not enough 7 and 6 produced in over short time, or?
Yeah, well, there are several problems with this. Of course, there's a problem of the how much your 207 peak is above the baseline, your mass spec, but then I would say you also have in laser ablation, I didn't go into this, but in laser ablation dating, when you don't use a multi-collector ICPMS, you have the problem of the common lead. So you cannot correct for the common lead because you cannot measure 204. And so that the zircon analyses who have a certain component of common lead, they are usually trending towards the right from the Concordia. So you just kick them out with your Discordia.
Yeah, I've never actually seen common lead in zircon using LA-ICPMS, provided, of course, you pre-ablate, which everybody does. The common lead should just be on the surface. As you mentioned before, zircon itself has negligible common lead, so that's really a big issue. Yeah,
it's not true. It's not true because when you have slight alteration of the zircon, you may see or you may not see in the seal.
Oh, that's true. Then you're really in trouble because you probably got lead loss.
I'm working now a lot in the
there may be inclusions too.
Yeah. No, it's a nightmare. Yes.
Yeah. Okay.
Can I add something concerning this discussion? So at University of Arizona and Laser Cron Center, we actually do control for 202 and 204 masses. The reason we do this is because 202 is mercury and it has an isobaric interference with 204 lead. And mercury is very much present in the helium, the carrier gas we use. So we do apply and correct for this isobaric interference. And then we also correct for common lead in this lab. And we can do this, as Urs said, of course, you need ion counters, right? And then another thing, based on your previous input, we do control for fractionation factors throughout the entire session, both 206, 207, and 206 to 38. And for each analysis, we do apply this like semi-linear correction. And the length of this heavily depends, as you pointed out, the downhole fractionation issue. The longer you ablate, the worse it gets, right?
Yeah.
So one way of circumnavigating this issue is also to ablate for a short amount of time, so that we never get like a very a pit that is too deep. And we usually point towards excavating less than half the diameter of the pit size. And yeah, depending on the spot size you have, this could have a larger or smaller effect. The spot sizes we can analyze here are 15 microns, even on a single collector element 2. And we can go even smaller, and these effects get minimized that way as well. And the third comment is also that while it's true that lead isotopes, you shouldn't be fractionating them in the instrument, we still control for these ratios, because the instrument, you still see a small variability between the 206, 207 throughout one single run. So yeah, those were a few comments that I wanted to make. And maybe I would like to end this comment just by adding that the 206 to 38 ages, I think that they are very useful, even in younger material. It's just that we have to be careful and not overinterpret and separate things that can't be separated. So whenever you need a higher resolution, temporal resolution, of course, you should always continue working with the crystals with the chemical abrasion ID-TIMS.
Yeah, I'd like to add one comment in
Go ahead,
support of
Kevin. Sorry, yeah.
So I've done a lot of comparative studies of the two samples, and I followed this discussion in the literature, and Urs did a great job presenting multiple details. And I just want to emphasize his point that you must anneal the zircons before you do laser ablation. It heals a lot of the crystal defects and makes the standards are almost always low uranium. They have very few crystal defects. And so the problem arises when you have a mismatch between the downhole fractionation of your standard, which you then apply to the downhole fractionation of your unknown, and that the rate at which it's digging can either be faster or lower. You often get dates that are too old from laser ablation, as well as too young. And that's because of this matrix effect. And if you anneal the zircons first, you've minimized that, and the variation in your laser dates becomes much tighter, much smaller. You still have lead loss, you still have a lot of the other factors, but that step alone improves the laser data immensely. And it only takes a furnace and 48 hours and some crucibles. It really should be adopted across the board. Every laser lab should be doing this.
Yeah. So are you aware of any systematic study, any published study? Because I was kind of successful.
Ben Howard went through the literature, and he put together some great plots. I was on his defense and insisted he put them in his paper. I don't know whether they made them into the paper. I haven't seen that Howard and 24 paper, but he did a great job of showing the relative effect of simply annealing and chemical abrasion, and the other thing that's really impressive about the annealing is that it changes it from a Gaussian normal distribution to more of a skewed it removes that population that are too old. And so it brings it down. The only factor you have left then is lead loss, and it even shortens that effect. These were on zircons that had been dated by both methods that he'd pulled out of the literature. So yeah, look at that. And if he hasn't published it, I'll raise it with him, because it was a great figure. I can share the figure for that matter that he had two or 3 years ago when he was working this up for his thesis.
Of course, there is a very important point. The primary standards we use for this. So in Lausanne, this is the JG1. This is a grain which is concordant. We have analyzed many times with CA-ID-TIMS, and is very absolutely non-representative for a natural zircon. It's extremely homogeneous. It's always yielding the same age, and is absolutely not applicable to a normal unknown zircon. So I don't know how many 10,000s of analysis they have, but they have an MSWD of 1.1 when you plot them all. So then we apply this to any other zircon in the world. So I mean, but I think this is a very good idea that this tail towards too old ages could be only due to ablation efficiency differences. Yeah.
Yeah, I would agree. The annealing is amazing. We do it now routinely, and I send a lot of zircons for pre-screening from ashes so that I can focus on the youngest grains, and it really improves the distribution of the data.
Yeah.
Another comment about chemical abrasion, as you said, it weakens the lattice. I did studies on the McAnee problem actually, and I chemically abraded them. The 7-6 ages seemed fine, seemed agreeable, but all the data plotted above Concordia. So the matrix had been damaged in a way that we were getting uranium loss relative to the standards. So it is tricky. I agree that we need to move in that direction, but I don't know the solution, because the chemical abrasion just changes the lattice too much, and then the laser doesn't work the same way it does in the standard, and you've introduced a problem then, especially for Phanerozoic, as you pointed out. You disturb the uranium lead ratio, you're toast as far as getting a good Phanerozoic date.
Yeah, I pointed out before, if you try this on zone zircons, the chemical abrasion, you can get a reverse discordance because of alpha recoil from the low uranium zone, from the high uranium zones, which are dissolved out into the low uranium zones. So your age may be a bit too young, the 7-6 age.
Yeah,
Okay.
It's complex. I'm going to have to leave, unfortunately. I have a meeting at 10:30, so I have to leave. But this is great discussion. Urs, we'll connect again by email. And Don, good to see you as well.
Sure. Thanks. I can show you a case. I had to take it out because of the time, but the case where it didn't work. So this is alpine basement, so we know exactly the story. You know, the old cores, Ordovician age orogeny, Variskin age orogeny, and alpine overprint. So had a master student who did dating untreated zircons of the same sample, untreated zircons, with a tail. This is stratigraphic age, so goes up, gets younger when it goes up. So tail to young ages, then 4 hours chemical abrasion, still the tail to 2 young ages, and then 12 hours chemical abrasion. The 2 young tail disappeared, but the overall scatter stays. So it's kind of still excess scatter and still much too young compared to the chemical abrasion. So actually, these are physical abrasion, chemical abrasion, CA-ID-TIMS states here. And the reason, when you look at these, so especially this one, this is a 4-hour chemical abrasion grain. All these triangles of white material here, this is all recrystallized during the alpine metamorphism. So we get rid of the rims. We know that they exist. These are alpine rims by physical abrasion. I learned many years ago from Don. and then we do not manage to get rid of this, because when we do chemical abrasion, these are perfectly crystalline, but alpine age probably. So this is a case, I would say, where we totally fail with our chemical abrasion approach. And it's just another message that it's really worth to look in detail at the CL images. Even only qualitatively, you can get an idea what you see.
What if you do annealing after chemical abrasion? Would it help to get back or resolve this problem that Kevin mentioned, that sort of after chemical abrasion for laser, it's too soft compared to standards?
No, you have to do the chemical abrasion before, because otherwise you leach the parts of the grain which are still at the first percolation point. You nevertheless start to leach these portions of the grains. And I think also there Don knows much more than me. You can actually fractionate massively uranium from lead by just leaching. I think the very first attempt they did just leach the grains and failed entirely. This was in the 90s. And we also tried in the lab when I was a postdoc at the ROM. I remember there was some trials, and we totally failed because we did this on a non-annealed lattice. So we had from the better crystallized portions, we had this selective leaching of some elements, and from the portions with higher degree of damage, of course, these ones we probably dissolved already. But you make a lot of artifacts when you do not. So really the breakthrough of Jim Mattison was to realize, okay, we first have to anneal to stabilize the portions of the grains which are at the first percolation point. This was the massive advance.
But what if you anneal twice before and after chemical abrasion? Would it help in terms of sort of making zircons more stable?
I don't think so, because it's not the question of that the zircon gets weak, gets soft or something. This is the question that it's only a skeleton left, it's very fragile. And sometimes, especially zircons like Don described, which have your internal high uranium zones, they completely fall apart. You have when you look in your microcapsule, you have 1,000 very, very small fragments you cannot handle anymore. And this is what remains.
Yeah, annealing doesn't actually restore the order of the crystal, except at a micro scale. If you have a zircon which is very low uranium, it's extremely hard to dissolve. If you put it, obviously in your leach, it would still be there. If it's high uranium and you anneal it, it will still dissolve, but more slowly than it would be in the disordered state. And it still dissolves because in the original crystal, you have one crystal, one coherent structure. Whereas when you anneal it, you're producing a lot of microcrystals. You're basically recrystallizing the grain, but not uniformly, so that you still have a lot of surface area in there in between the crystallites where it can be attacked. We tried this on norite zircons from Sudbury, which are like 1,000 ppm. And if you anneal them, they can still be dissolved basically virtually completely within minutes because they're so damaged, and because even though you've recrystallized them and restored the Raman peaks, then you've basically still got a mass of microcrystals with a lot of potential surface area to interact with the dissolving fluid. So it doesn't completely remove the damage. And annealing it again, I don't think would do anything. Basically, it probably very quickly goes to its most stable state.
Thank you.
All right, great. So we came up on 90 minutes on our recording. So these are sort of time I like to cut it at. So let's go ahead and thank Urs again. Thanks a bunch. Really great talk and great discussion.
Yeah, it was great discussion. Very nice to see you.
Thanks. You probably had the largest crowd, one of the largest crowds we had. So obviously there is a lot of interest in applying chronology, and we will continue. And next week we will have another chronology presentation based on TIMS from MIT. So stay tuned and join us next week.
All right, see you all.
Thank you.
Great talk.
Bye.